The global acceleration of electric vehicle adoption is a major environmental milestone. Every year, millions of drivers switch from internal combustion to battery power, significantly reducing the carbon footprint of our transportation. However, this shift reveals a massive infrastructure challenge. Most local distribution grids were never designed to accommodate the heightened and irregular power demands required to charge millions of vehicles simultaneously. The crisis point occurs every day at 6 p.m. As commuters return home and plug their cars in for the night, they create a massive synchronized spike in electricity demand, just as residential energy use is already peaking. This diagram shows the scale of that draw. A typical home has a relatively low, steady power demand, but activating a single 7.2 kilowatt charger creates a sudden, massive spike. One car can pull more power than an entire household's baseline needs. When thousands of households follow this same behavioral pattern, the sudden surge can exceed the capacity of local equipment, turning a milestone for decarbonization into a threat to grid stability. The impact is felt most acutely on low-voltage distribution networks, the final stage of the grid that delivers power to our residential streets. This network map illustrates the sensitivity of local infrastructure. Engineering data shows that just a 10% increase in EV adoption causes a 14% increase in the load on residential transformers and cables. As these capacity limits are breached, transformers can overheat and fail. Furthermore, the high draw causes voltage drops at the far ends of the power lines, potentially compromising the power quality for every home on the block. Treating an EV as a simple consumer electronic overlooks its reality. These are industrial-scale loads parked in suburban driveways, necessitating a total system transition. The same battery density that threatens to overload the grid also represents the largest untapped resource for stabilizing it. The average electric vehicle carries a 60 to 100 kilowatt-hour battery, roughly 6 times the capacity of a standard home storage unit. Yet these vehicles sit idle and parked 95% of the time. This diagram illustrates bidirectional charging, or V2X. It allows energy transfer to become a two-way street. Instead of only consuming power, electricity can flow from the car to the house, or directly back into the broader power grid. This capability transforms a parked car from a passive drain on the network into a dispatchable energy storage asset that can support the grid during peak times. Managing millions of mobile batteries without causing network chaos requires a unified communication framework. This DOE architecture shows the communication pathways. ISO 15118 establishes a secure handshake, negotiating vehicle-to-charger power flow. OCPP 2.1 manages the cloud backend to monitor metrics and deploy profiles. Finally, OpenADR lets utilities command cars to dispatch power during grid stress. This 3-tiered stack allows grid operators to safely orchestrate a decentralized network of mobile batteries as a single coordinated resource. For the individual vehicle owner, bidirectional hardware redefines the utility of car ownership, beginning with vehicle-to-home power. During a blackout, a fully charged EV can act as an emergency backup, powering an average home's critical systems for 3 to 5 days without a lifestyle compromise. There is also a financial incentive called energy arbitrage. Owners can buy cheap electricity overnight when demand is low and sell that same stored energy back to the grid when prices peak in the evening, as shown in this rate chart. This turns the vehicle into a revenue-generating household utility, helping to offset the initial cost of ownership. When thousands of these vehicles operate together across a region, the scale of their impact moves from the driveway to the macro grid. This is the virtual power plant. Grid operators can pull tiny fractions of energy from millions of aggregated cars to balance the system during massive demand spikes. This system allows aggregated EVs to absorb excess solar generation during the day and deploy it at night. This directly replaces the need to fire up fossil fuel peaker plants to meet evening demand. The electric vehicle has evolved into the decentralized power plant required to support a renewable energy future.